So far, we've been developing a bag of tricks for solving differential equations. Included in our bag is separability, the concepts of exactness, we also found the general solution for any linear first-order ordinary differential equation. But how about this differential equation? dx dt is equal to x plus t squared minus 1. Well, it's not separable, it's not exact, and it's not linear. So does that mean we just can't solve this differential equation? It seems very simple looking. Well, it turns out there's one more set of tricks that are useful for solving ordinary differential equations, and that's the idea of substitution. So consider our differential equation again. So let's let u, a new variable, be x plus t. In that case, du dt is dx dt plus 1, or rewriting that dx dt is du dt minus 1. So we can rewrite our differential equation as du dt minus 1 is equal to u squared minus 1, or that simplifies to du dt is equal to u squared, which is separable. So we can solve this using the usual techniques of separability, and we find u of t is minus t plus 1 over t plus c. We can convert this in terms of our original variable x of t, where x is equal to u of t minus t, and so x of t for its solution is minus 1 over t plus c minus t. So that's our general solution using the idea of substitution. So the whole idea of solving a differential equation by substitution is the following. First, you define a new variable in terms of the old variables. Second, you rewrite your differential equation in terms of that new variable. Third, you solve the differential equation, presumably you can solve it now. And 4, you then convert back to the original variables to get the solution that you were interested in. So as another example, consider this differential equation, dx dt is e to the x minus 2t plus 2. So let's use substitution. A good choice is u is equal to x minus 2t. So du dt is dx dt minus 2, or we can rearrange that for dx dt. And plug this into our differential equation to get step 2, which is our differential equation in the u variable. And again, this comes out to be something nice and separable. Du dt is equal to e to the u. And so we can solve this directly by using separability. So they take the integral on both sides. And we find that u is equal to minus natural log of c minus t. And putting that in terms of our variable x, original variable, we get x is equal to 2t minus natural log of c minus t. So this is the general solution to the problem we were after. So looking at this, you might ask, how do we know what substitution that we should make? Well, the short answer is you don't. You just make a good guess and hope it works, and if it doesn't, you try another one. Sorry, it's not that much better for you than that. Let's consider another example, one of population dynamics. So as we know, humans require a partner to reproduce. And so what that means is that the birth rate is proportional to the number of couples that can be made, or in other words, the number of people squared. The death rate is, of course, proportional to the number of people that there are. And so if we want to know or find the number of people as a function of time, we can set up a model to do so. So a model that we might use to understand this is, let's let y of t be the number of people as a function of time. Then y of t satisfies the differential equation that the rate of change of y, the function of time, is equal to a times y squared, which is the birth rate, minus b times y, which is the death rate. So this is a separable differential equation, so we could solve it that way, but the integral is actually kind of hard. So let's try using substitution to make this into a linear differential equation. So let's make a substitution u is equal to 1 over y, so that du dt is minus 1 over y squared dy dt. Or I can rewrite that in terms of dy dt, so dy dt is actually minus 1 over u squared du dt. So we can rewrite then our differential equation, and it becomes minus 1 over u squared du dt is equal to a over u squared minus b over u. Putting this in standard form, we get this nice looking linear separable differential equation, du dt is equal to bu minus a. So we can solve this using the techniques of separability, which we should be comfortable with by now. and find that u is equal to c e to the bt plus a over b. In terms of our original function, which is the number of people, y is a function of t, which is just 1 over u, then we get y as a function of t is 1 over c e to the bt plus ab. A typical behavior for this would look like the following, namely if you start close to 0 for y, it eventually asymptotes up to the critical point of a over b. So this turns out to be a very special case of a very famous form of equation, differential equation, called Bernoulli's equation, which has this form. It almost looks like an inhomogeneous differential equation, except it has this nonlinear term. It's also not separable in general, and it's not exact. But this equation can be solved by substitution. If you make the substitution u of x is equal to y of x to the 1 minus a, then after a bunch of algebra, you get a differential equation which is nice and linear, and in fact it has the form of an inhomogeneous linear first-order differential equation. So this equation can actually be solved. We can use the techniques of inhomogeneous differential equations to solve this differential equation, although we won't write down the details here because it would still be implicit in terms of p of x and g of x. So this is the power of using substitution.